When light hits certain metal surfaces, it knocks electrons completely free from their atoms, sending them flying out into space. Late 19th century scientists knew these photoelectrons were popping off the metal, but they faced a massive logistical problem. They had no reliable way to measure how fast these tiny, invisible particles were moving. To figure it out, they turned to the high-tech workspaces of the era, laboratories completely dedicated to shooting electricity through gases at low pressures. The main tool of the trade was an evacuated glass tube like this one. It housed two metal plates in a complete vacuum, a photosensitive emitter to release the electrons, and a separate collector plate to catch them. By hooking these two plates up to a battery, experimenters could create a customized electric field between them. That field could either pull the flying electrons forward or violently push them backward. By simply turning a voltage dial, scientists took a chaotic, invisible spray of particles and wrangled it into a precision-controlled stream they could finally measure. When the battery makes the collector plate positive, it creates an electrical downhill slope. The positive plate acts like a powerful magnet for the negative electrons, accelerating every single one of them toward the finish line. As you crank up that positive voltage, the electrical current flowing through the circuit rises rapidly, but it quickly hits a hard limit where every single electron knocked loose by the light is successfully captured. This chart plots applied voltage against the resulting photocurrent. The line rises, then levels off into a plateau called the saturation current. This is the maximum electron flow, achieved when the field captures every emitted particle. Notice the line stays perfectly horizontal as positive voltage increases. The metal sheds a fixed number of electrons per second, so extra voltage cannot summon more current. While the saturation plateau gives us an exact head count of the electrons making the jump, it tells us absolutely nothing about how much kinetic energy those particles actually possess. To find their energy, we have to flip the battery's polarity. Now the collector plate is negative, which repels the incoming electrons, forcing them into a steep electrical uphill climb. We call this a retarding potential, a negative voltage applied to the collector plate that actively slows down and repels incoming electrons. It acts as a strict physical filter, where only the absolute fastest, most energetic particles have enough momentum to reach the plate. Look at what happens to the data when the voltage dips below zero. The current plummets because slower electrons lose their momentum and are pushed back to the starting line. Eventually, the curve hits the horizontal axis. At this precise negative voltage, the climb is so steep that even the most energetic electron is stopped dead and repelled just before contact. This critical threshold is called the stopping potential, denoted as V0. It is the exact minimum negative voltage required to bring the photoelectric current completely to zero, acting essentially as an invisible electrical wall. By finding the exact voltage that builds this wall, we measure the maximum kinetic energy of the particles. The electrical work done to stop that final fastest electron translates perfectly into a simple equation. The maximum kinetic energy, K max, equals the elementary electron charge, E, multiplied by our stopping potential, V0. By reversing the field, physicists successfully turned a simple negative voltage reading into a highly accurate radar gun for the fastest particles in the stream. This setup immediately led researchers to test an assumption derived from classical physics. If you shine a light that is 3 times brighter onto the metal, will those electrons absorb 3 times more energy to climb the hill? When you dial up the intensity of the light, the metal responds instantly by releasing a much denser flood of electrons into the vacuum. This chart shows saturation currents for 3 light intensities. The brightest light, I3, creates the highest plateau. As we apply a negative retarding potential, all 3 curves, despite massive differences in electron volume, plunge and crash into the exact same stopping potential point. Brighter light gives us a larger total number of electrons, but it does not give us faster electrons. This single point of convergence proved that light energy doesn't wash over the metal continuously, but instead arrives in rigid, discrete packets, what Albert Einstein would later define as photons.